Okay, so we can start the second half of today's exciting lectures. And it is my great pleasure to welcome Elon Lindenstrauss of the Hebrew University of Jerusalem. And he will speak on arithmetic aspects of diagonalizable flows. So please.
Thank you. So Peter helpfully remarked before my talk that I have a high bar somehow. A high bar was set by the previous speakers that would be very hard to meet. But in any case, it's a very great honor to speak here in this conference. It's really a remarkable meeting for a remarkable person. It's also, of course, a great honor to be introduced by Marina Ratner, whose work really shaped the field, and which you would see why in a few minutes. I first met Peter, or at least first had some serious mathematical discussions with Peter, what seemed like a couple of years ago, but I sort of was shocked to discover that when I first met Peter, he was roughly my age now. When I was a postdoc coming to the Institute of Advanced Studies. I was sort of in a transitional period in my career. It's, of course, usually what happens when you finish your PhD, but I also changed fields. I was sort of working in some classical algorithmics here, and I was sort of moving towards flows on homogeneous spaces with the hope of getting applications to number theory, though my understanding what this phrase is has evolved since then quite considerably. I guess mostly thanks to Peter, and if you add Peter's student, then that statement is becomes even stronger. So I think it was new custom at the time. It's probably now a long tradition that new postdocs when coming to the institute give very short 15 or 10 minutes talk each about what they do. And somehow following that, I was talking about a paper, my first paper on homogeneous dynamics, which was joint with Barak Weiss, which we sort of actually wrote while babysitting Barak's kids, which he handled as an editor actually in a journal. And after my talk, he gave a suggestion which seemed quite far-fetched at the time, maybe still seems far-fetched, to try to find applications of these techniques to quantum unique ergodicity. And I guess one advice I can give to people is that if Peter gives you some comment, some advice, some suggestion, it should be taken very seriously. I'm happy to say that I took this advice very seriously, and it has really in addition to eventually leading to a nice theorem, it also, on the way, I sort of really started to understand how the various structures on homogeneous spaces interact, the spectral structures, the arithmetic structure, and the dynamical structure. Actually, one thing which helped Peter can be, on the one hand, he's sort of extremely, it's sort of somewhat of a contradiction, right? On the one hand, he's sort of very generous, very kind person, very much likes to help people. And on the other hand, he is quite tough. And somehow this combination was very good for me because one thing he forced me, so I found some kind of tentative connection between these two things. And he sort of forced me to understand it, to sort of pushed this understanding to a limit, which was very important. Forced me to understand something that I wouldn't have understood otherwise. I probably don't want to keep all of my 50 minutes talking about Peter, though. But it's fun to talk to Peter. I mean, some people, when you ask them a question, they answer the question to the best of their abilities. With Peter, sort of, he answers your question. He answers some related questions. He tells you what was the question that should have been asked, and then tells you a few other interesting things he have recently heard. And I mean, that's somehow, it's really a privilege to talk to him. It's a privilege that is quite rare because I'm not the only one who discovered that this is a way to learn great things. Anyway, I've greatly, even since then, I've sort of often relied on Peter's advice and learned a lot from Peter. What amazed me is that somehow I'm not so unique in that wherever I go, I find people who sort of tell me that Peter had a decisive influence on their career, and that's really unique. Okay, so this is must speak is good. So I'll talk about the result. This result is, so the result I will get to in the end, there's some results here. The result I'm going to go to in the end is not a new result, unlike other speakers, but it's sort of not so well known. And for me, I think it's the most, it's the application of diagonalizable flow that I am most happy with somehow. I guess one reason why this application is not so well known is that we never quite stated it explicitly. So I'll try to do it here. So let me start with the setup. Once I was speaking in a conference, and Zeev told me that I should avoid Adele's like the plug. Well, he's not in charge now, so I'm starting with the Adele's. Like the plague, yeah, okay. That's somehow my Israeli accent. So he's not in charge here. I'm starting with the Adele's. So this is the setup, the fancy version of the setup. And I know that this audience is very mixed because Peter's research interests are very mixed, so this brings people from various backgrounds. I'm trying to make it somehow accessible quite widely. The Adele's are some kind of object which are a product with some restriction of the real numbers and every other completion we know of the rational numbers. And the one thing which is nice about the Adele is that they're a locally compact ring, and the rational numbers sit inside them in a natural way discretely. And then if you look at some group defined by some equations hopefully defined over the rational numbers, and you look at the group at the adelic points of this group, divide them by the rational points, you get a quotient, which in my case, I've assumed my group is semisimple, has a finite invariant measure. And there's sort of a lot of interesting things you could say about the measure, but not the way I look at it, because I'm going to normalize the measure to be 1. Now, okay, that's a fancy version, but it's sort of maybe it's also a good idea to have a less fancy setup. And to begin with, this less fancy setup would be quite adequate, and I would stick to it. Eventually, we would have to become fancy, and then I will go back to the Adele's. So now I'm taking a group, again, the same group, and instead of looking at all possible completions, only choosing a few. I mean, I'm somehow, according to my mood, I set a finite number of completions I want to take, and I'm looking at the product of the real points of the group and the p-adic points of the group, several p's. And I'm taking a congruence lattice in it, basically, essentially the integer points in an appropriate sense in this group, and it becomes a lattice discrete finite covolume subgroup of my group, and then I have a quotient which has a finite measure. Now the setups are closely connected. Morally, basically this less fancy setup is a more fancy setup when I forget some information, when I forget some. There's a projection between the fancy version and the non-fancy version with compact fibers, which initially are not going to matter for us. So let me talk a bit about homogeneous dynamics. And I'm not going to give a full lecture about homogeneous dynamics, but let's start with sort of just one object, which is interesting both dynamically and number theoretically and from many other perspectives. If I have some subgroup, I have a quotient, G mod gamma, I have a subgroup H of G, and I'm looking at an orbit of this group H. Now, what would it mean for this orbit to be periodic? There could be some disagreement, but for me, an orbit is periodic of a big group if it has finite volume. If the stabilizer of my point inside the group has finite covolume in H, or in other words, if on this orbit I can put a probability measure that is invariant by my group H. That's a natural definition. And here's one basic question which I'm going to somehow limit myself as far as dynamics and looking at this particular question. Has a long tradition in dynamical system. Suppose I have some sequence of periodic orbits, and I'm actually being a bit general here. I'm allowing the group that the acting group to change each time, and then sort of the base point changes. And okay, let's assume a bit more. Let's sort of, just for simplicity, assume that there's some point in each orbit which converges to some limiting point. That's sort of usually a mild assumption. If this doesn't happen, then basically, if this doesn't happen even after you pass through a subsequence, this basically means that your whole orbit goes to infinity. So I have here a sequence of measures now, right? Each periodic orbit, by definition, attached to it is a measure. And I am looking at some limit of the measures. And I sort of wonder if this limiting measure converges to some nice measure. Convergence of measures in the weak star sense. So basically what I want, if I have a sequence on some space, locally compact space X is locally compact. And if I have a non-locally compact space, I run away. So I have a sequence of measures on locally compact space. They converge to some measure if for every f inside, which is compactly supported continuous function on X, the integral of f with respect to these mu i's converges to the integral of f with respect to mu. Okay. Now, of course, one thing, I've assumed that my groups, they may be changing, but there's only a group, at least sort of a connected group like I'm looking at, is determined by the Lie algebra. Lie algebra is point in a Grassmannian, the Lie algebra of a group. So basically, there's only compactly many groups. So I'm assuming that the groups would converge to some limiting group. And then the limiting measures would become invariant by this limiting group. And this leads us naturally to study what invariant measures do exist. And I repeat the definition that the probability measure is invariant if, by some group, if I take every element of my group, I push forward my measure by left translation by my element H, and I don't change it. Now, those are invariant. There are special of these. So these invariant probability measures are a compact convex set. There are special points of this collection, the extreme points of my convex compact set, which I call ergodic. So there are other definitions of ergodic which are maybe more natural, but for our purposes, this one would do. Okay, so they are ergodic. All measures are the ergodic measures, which are the extreme points. And there's a general theorem, Choquet's theorem, that you could write any invariant measure as average of ergodic measures. This is the weak form of ergodic decomposition. Ergodic decomposition says a bit more. You could also divide your space somehow, but that's good enough for us. So now I'm getting to this truly remarkable theorem of Marina Ratner. So the form I'm giving, the S-arithmetic form, so originally Ratner proved her theorem for real Lie groups. I'm only talking about algebraic groups, but sort of real algebraic groups are also, in particular, Lie groups. And then it was extended to general S by Ratner and Margulis and Tumanov. So suppose I have a group, suppose my group H, which I'm looking at, this limiting group, is generated by one parameter unipotent groups. So let me remind you what a unipotent element is. So if I have a unipotent element, it's anything I can get by exponentiating a nilpotent element of the Lie algebra, if you wish. Right, so that's a unipotent group. Then there is so I have a measure which is ergodic. Then it only comes from basically a simple algebraic construction. There is some group, possibly bigger group, possibly equal to H, so that mu is the natural measure on a single periodic orbit of this group L. And in the arithmetic case, and that's actually quite important in application, so I'm just saying it for general knowledge, you could say a bit more. You could say that L is up to conjugation a finite index subgroup of the points of the S-arithmetic of the QS points of a Q group, of the group defined of the real numbers, which is not any group, but it's a group that is generated by unipotence over the algebraic closures. That's sort of an important. Now, that sort of, originally I said that the original dynamic problem I posed was about behavior of periodic orbits in the limit. There's a beautiful theorem of Moses and Shah, which is also based on work of Dani and Margulis. And of course, at the end, would be reduced to the measure classification, which is sort of the main ingredient, but there are sort of quite substantial ingredients in the reduction. That essentially says that if I have a sequence of invariant, sequence of periodic measures, they would tend, and they would go to some limit, let's say. This limit would be a nice measure. It would be a measure, it would be ergodic to begin with, which is far from automatic. So it will be one of these measures that you get from Marina's classification. And moreover, not just essentially these periodic measures that you have live on this limiting, on the support of this limiting measure. So you could get something about the limit directly from the measure classification theorem, with some kind that any limiting measure would be some kind of average of nice measures, but you get much more here. And if you sort of did care to look at the fine print of what I wrote, you would see that if you have a sequence of measures, a sequence of invariant, a sequence of periodic orbits with the orbits tending to, the measure of the volume of the orbits tending to infinity, in more or less any reasonable sense you would like to measure that, then the limiting object would in fact be a periodic orbit of a group which is larger, which have larger dimension. Now, in fact, I think the first arithmetic application of this result, which sort of appeared before the result, but that's sort of a minor detail, is a very beautiful one by Burger and Sarnak that discusses equidistribution that discusses equidistribution of Hecke points, which then led to much further work, including work by Eskin and O, and sort of from a different perspective, there was a paper by Clozel, O, and Ulmo, but I think this is sort of a really pioneering application, and actually, sort of in some sense, the first is somehow, in some sense, something which is sort of very influential. The second is something which is only now beginning to have some kind of sort of more impact in the dynamical systems world. But the first case of this theorem that I quoted about periodic orbits is actually, for SL2R, is actually a theorem of Sarnak. And the proof is actually quantitative and uses Eisenstein series. And if you quantify it a bit more, you probably get Riemann hypothesis. So that's maybe there's some difficulties if you really want to quantify it some more. Okay, so that was about invariant measures, but now I want to talk about a different case of invariant measures. So the groups I covered up to now were groups generated by unipotents. What about if my group is not generated by unipotents? And more or less, the interesting case is diagonalizable groups which are, and every such diagonalizable group, you could, so I'm looking at, let's say, subgroups of maximal split tori. And so there's a measure classification result. It's not complete, it's a partial result. But it's also still quite, apparently quite substantial. So it doesn't, this theorem that I'm giving you doesn't talk about a general diagonalizable group. What I want is basically taking a maximal split tori in my group G. G is a product of my group over R and my group over periodic numbers for various primes. And so if I have such a group, intersection of maximal split torus with a normal subgroup of G, and if the dimension is at least 2, then and if I have a measure which is invariant and ergodic under this action, which doesn't live on a smaller, on a periodic orbit of a smaller reductive group, in which case you could sort of, why work with G, work with a smaller reductive group, then either my measure is a uniform measure, which is sort of the main case, or, okay, there's something which is not supposed to happen ever, but we don't know how to show that it doesn't happen ever, that my measure is very small somehow. The transverse to the centralizer of my action dimension of my measure is 0. Okay, so that's the theorem. There's an obvious conjecture. But, and there was this restriction that the dimension of the acting group has to be at least 2. For dimension 1, this is completely false. And I guess the key insight, which was made independently by Cassels and Swinnerton-Dyer and by Furstenberg, is that this dimension thing is sort of changing the situation dramatically. The theorem sort of, if you have a general ergodic and invariant measure, you could look at the smallest reductive group whose orbit supports my measure, and then a reductive group is basically a product of a torus and some simple groups, and, or maybe in my context I would say Q almost simple groups, and you treat each one separately. What you probably should have, I should have said in my previous slide that my group G is not just semi-simple, but it's Q almost simple. Okay, so the lattice would be irreducible in it. And then you could essentially take any arbitrary measure and write it as a product of three measures. One which is invariant, one which has zero entropy, one which sort of actually product of many things of rank 1. This theorem is sort of a first measure, lots of first measure classification theorem in this direction. The first measure classification theorem in this direction is by Katok and Spazier, following some work of Rudolph. But the great advantage of this theorem is that it can be used for number theoretic applications. And so I didn't say actually whose theorem this was. So it's the theorem I stated is by Einsiedler and myself, but it's sort of based on earlier works, let's say, by Einsiedler, Katok, and myself. And actually, for the applications, I'm going to talk about the original, so the paper by Einsiedler, Katok, and myself, which has a relevant measure classification result. Now you could look at the periodic orbits, and for the periodic orbits, in this situation, there's trouble. I mean, it completely doesn't satisfy what we want. I mean, I'm running a bit. There are periodic orbits, and I guess this was already observed by Cassels, but we meaning Einsiedler, Michel, Venkatesh, and myself, learned this from Sarnak, that there is a sequence of periodic A orbits with volume tending to infinity, which escape every compact, which sort of are all attached to points very close to the identity, but which give zero measure to any compact set. This is something that's completely unheard of in the unipotent world. And okay, I don't know how to show it, but it's undoubtedly true in a fairly strong sense that whatever periodic orbit you start with, you could find periodic orbits which have nothing to do with this periodic orbit that would somehow in the limit give positive measure to this arbitrary periodic orbit. So let me just reformulate the question. Instead of talking about periodic orbits of A, I want to somehow make the Q structure, the structure of the rational structure, more apparent. So an orbit is periodic. Let's try. An orbit is periodic. Well, it means that the stabilizer of my point is co-compact in A, which exactly means that this group here, the intersection of my lattice with some shifted torus, is big. And this basically means that this shifted torus is an arithmetic object. Is given by those matrices which commute with a given set of integer matrices. So, and okay, if you want to be technical, it's not just a Q torus, it's an anisotropic Q torus. It's sort of one which is not split over Q, but split at every place inside those sets of places which I look at. And you'll notice there's a condition here. I want my acting group to have dimension at least 2, which translates to either n being at least 3, or the place looking at least 2 places. One more thing I would like to say. So basically, I have instead of looking at my periodic A orbit, I can basically look at a shift, normalized shift of a Q torus. Also from this construction, you see that these periodic orbits are very number theoretic objects. In particular, to any Q torus, you could attach a number field. You basically take the collection of rational matrices which commute with this Q torus. This gives me an embedding of a number field inside the algebra of n by n rational matrices. So now I need to somehow move this big circle around. It sort of brings the dells from behind the blackboard. So I have the adelic group, and I have the S arithmetic quotient. which is, like I said, a quotient of, so this S-arithmetic quotient is a quotient of my adelic space by some compact group. So it was a natural projection between these two. Now, the key point is that if you take an adelic torus orbit, you take the adel points of a torus, and you look at, and you project them to sort of this less fancy setup, you sort of get a surprise, which is something that I guess Gauss already understood in some sense, in his, probably in a stronger sense than, anyway, in a very strong sense, but not explicitly. You don't get just one periodic A orbit. You don't get just one orbit of my, you don't just get the S-arithmetic points of your Q-tors, but in fact you get somehow, as a package deal, a few other torus orbits. And at least for some orbits, I mean, the number of orbits you get is some class number, and here's the explicit way why this is a class, why this is a sort of the class number. You could look at a slightly more general situation. You could look at, instead of the algebra of n by n matrices, where if you look at the invertible elements of this algebra and you divide by the center, you get PGLN. I could look at any center simple algebra, any algebra of of degree n, where the center is just my ground field. And I could look at the algebraic group you get by looking at the invertible elements of my algebra divided by the center. So most places you get that if you tensor my algebra with, if you look at the algebra and replace the coefficients, instead of having them rational numbers, you put in them periodic numbers, you get actually the algebra of n by n matrices. And I'm going to fix some finite sets in which my algebra splits. So, okay, I'm reminding you of the setup here. And what we, sort of to summarize this discussion, if I start with a Q-tors, I start with this algebraic object as Q-tors, a diagonalizable subgroup of my, diagonalizable over the, let's say, algebraic closure subgroup of my group, which you could define as things which commute with a given set of rational matrices. And if I start with some kind of model, what I would like, how I would like, I mean, I'm basically going to consider many of these rational toruses, and sort of each one, like people, like each one has their own opinion how it should look at various places. I need to somehow install some order in them. So I'm going to choose more or less arbitrarily a maximal torus in each local group, AV, in one of finitely many places. And then I'm going to define a shift, which in these finitely many places, I'm going to take my Q torus and shift it, and the rest I'm going to leave. And then I get some kind of, then I put some kind of order and discipline on these Q tori. I can normalize them in a way that's sort of easier to compare them. And I get a collection of, this is sort of the basic objects that I want to talk about, are these S-normalized adelic torus orbits, which if you look at them, if you sort of don't like adels, you look at them as inside some S-arithmetic quotient, they're just a finite, slightly mysterious union of periodic orbits of my of the group A. And the basic question is, I'd give you a q torus of a large height, and I shift it by some g. How does it look like, right? You have some questions, Ev? I am repeating, I'm going to explicitly, but he was doing it more in a slightly more friendly way. But I'm actually repeating both of your talks. So assuming my, so basically I want to understand if I have a q torus of large height, how is it, and I shift it, how is it distributed? And okay, I mean, there's sort of a question. So in so one of these talks that set very high bar, Bill Duke's talk, he was looking at some collection of Q-tor, and he sort of had two cases, one where the discriminant is positive, one where the discriminant is negative. So if I sort of fix some finite set of places, maybe not including infinity, and I decide how I want my fields to split, maybe I would like, in this finite set of places, my torus to split completely. So the question essentially reduces to the S-normalized case. That's somehow the hardest case. You see the sort of various, I put a star, I put I think. I mean, this is somehow homework I should have done before giving this talk to make this precise statement, which I haven't. And it's sort of, it's a non-trivial issue involved, but it's a non-trivial issue that smart people have specifically Moses, Eskin, Moses, and Shah have sort of dealt with. So I think it's essentially what I'm saying is correct. Anyway, what I'm saying is correct, but this essentially I think is, you could hopefully ignore. So special cases, if I just take very special cases, if I take 2 by 2 matrices, I take PGL2 or SL2, I think it's probably, to be pedantic, Bill Duke in his talk talked about SL2. And you take the torus to be the thing which preserves a integral quadratic form, which in order, if you want to split at infinity, then you should take the discriminant to be positive. And then you project everything to the real group. You would get, so the projection of a normalized adelic torus, this kind of object that I was considered, this normalized adelic torus, would be a packet of aperiodic orbit, would eventually be exactly the collection, if you project to the hyperbolic space, would be exactly the collection of periodic geodesics that we had nice pictures of in Bill Duke's talk. And then Duke proved quantitative equidistribution of these geodesics. And there are sort of partial results by Linnick and Skubenko, which were also sort of quite remarkable considering when they were proved and how they were proved. If you take another highly respectable division algebra, the Hamiltonian quaternions, and you do this construction, so it doesn't really fit in what I said because, well, over the real numbers, the group of units of the quaternion algebra are not are a compact group, but you just formally do this thing, and you look at what these normalized adelic torus orbits mean. They just mean something very, very simple, which you also saw in a previous talk. Also had very nice pictures of, and that's integer points on a sphere. That was the subject of the Ev's talk. And again, equidistribution is a theorem of Duke. I think in this case, and you could correct me if I'm wrong, the actual estimates needed are due to invariant, and there's a partial result by Linnick. So now, the theorem that I want to mention, then I would stop using this. I would sort of keep the theorem displayed up, and I'll try to explain a bit about how the theorem is proved, why it's related to what I've said so far. But let me try to explain the theorem first. So I'm taking a division algebra, and essentially, I think for division algebras of degrees 2, I won't be able to say anything that is not covered in a much stronger way by the analytical sort of automorphic forms techniques, subconvexity techniques. But okay, formally, what I need is again at least rank 2 in some sense. So I'm taking a division algebra, which let's think of as being of degree at least 3. A division algebra now, not a general central simple algebra, division algebra. I take a finite set of places, and I'm assuming that my division algebra splits at this finite set of places. So basically, if I allow the coefficients to be inside the p-adic numbers for each p in this set of places, maybe p including infinity, where the p-adic numbers means just the real numbers, that this is going to be isomorphic to the algebra of n by n matrices. So I have some finite set of places, and I'm taking the algebraic group that was not supposed to come now, but anyway, not a big surprise. I'm taking the algebraic group that corresponds. And now I take the adelic quotient. This is a very nice space. I take any open set inside this adelic quotient. I have no restrictions over n. In particular, one thing which is nice, that you could definitely take n to be a composite number, which is an issue often. So if I take an open set, I can give you, well, actually I can't really give you because it's not effective, but non-effectively I can give you a list of finitely many fields, finitely many number of fields of degree dividing my degree of my division algebra. So that if I have any anisotropic Q-tors, which splits completely at each one of these places I took, and then I look at the associated normalized adelic tors, sort of normalizing things after in the fashion that was done in Duke and Linnick theorems. And if these associated normalized adelic tors avoids this open set omega, then the field, you could say much stronger thing. This is sort of a weak form of the theorem, but in particular, the field which is associated to this Q-tors is, if n is prime, just has to be one of finitely many fields in my list. And if n is general, then it at least has to contain a subfield in this list. Okay, so that's somehow the theorem. And I'll try to explain a bit the steps in this proof. And I think in my abstract I mentioned there was a question somewhere?
So just to pass it back into language which other people use. So in the classical case, this is a weak form of the distribution. In the classical case, it says that if you have,
It's density.
Set and this omega compact set in the fundamental domain, and you have geodesics, and then the closed geodesics which don't intersect it.
It's a density statement.
It's a density statement?
It's a density statement.
I thought it's a finite. So you're saying it's weaker than that?
No, it's density would, if you parse what density means, it means that if
Yes,
you have
it's a
a avoid a
density,
give, it's a density
so
statement.
This compact set is only finite.
It's a density statement.
Discriminants that can do that.
So in my abstract, I sort of said something sort of this, in some sense, so I don't think there are any competing technology available at the moment to study orbits of such small groups. So Manjul has sort of very powerful technology, but he only looks at sort of He can not a particular field, to look at some kind of averaging over fields. So in this context, I don't think there are competing technologies at present. On the other hand, there are some limitations of the field, which there are some limitations which somehow, whenever both Bill Duke and I, or whatever, any one of the automorphic people or I can prove the same theorem, obviously that there would be no competition, and their theorem is much stronger. So for once, I need to assume some fixed splitting conditions. That's sort of inherent in the method. The only way you could get an ergodic argument to work without some kind of splitting condition, well, there's two things. One, you could hide them under the rug, like sort of, we didn't try to do it, but somehow, in some sense, this is what happened in regarding our proof of this equidistribution of geodetics. You sort of swipe it under the rug, somehow hide it in the statement of the theorem. That's one way. Another way, which is sort of much more profound, is if you could get some kind of quantitative equidistribution statement. If the quantification is good enough, then you could avoid imposing some splitting conditions. That's sort of really, I think, substantial work that's sort of started with the work of Einsiedler, Margulis, and Venkatesh, and now there's probably, perhaps, even now as we speak, was posted a version by in sort of a sort of souped up version by Einsiedler, Margulis, Muhammadi, and Venkatesh. And that's sort of, I think, sort of, but that's sort of very significant. But if you don't have any kind of quantitative statement, then you have to fix some splitting condition. Moreover,
excuse me, this is using, you said effective, yeah, because you're using more effective words with more.
no, I'm saying non-effective. I said non-effective.
Well, I thought you said it's not effective even for density.
It's not effective even for density. To begin with, it's not effective because I have to rely on the Siegel estimate, whatever I do. So I don't know. This is actually something you know better than I do. Perhaps for some number fields, you know the regulator effectively, but in general, it's ineffective just from the starting point, just to know that there are points is ineffective. So before I know that there are points, I can't prove that something is dense. Okay. And then less essential in some sense, the ergodic theoretic statements are not stated in an effective way, and sort of it's sort of, okay, sort of there's some fun in getting them to be effective, which, anyway. So this is non-effective. I was sort of trying to emphasize that it's non-effective. And the other thing is that somehow, typically, if you prove something using dynamical techniques, you get no rate, which is perhaps even a worse problem than assuming the splitting condition. But like I said, these things are in some sense, these two deficiencies are in some sense related. So what is happening here? So if you remember, I have this GA modulo GQ. And I have a finite set of places on which I'm looking at, and maybe I have a bigger set of places where, so there was this finite set of places where I assumed that my Q-tor split, and maybe, for instance, if infinity is not included in the set of places, I want to work in a set of places which include infinity. So I have here some set of places, and I'm looking at the projection and of my Adelic quotient to my S-arithmetic quotient. And there's actually no, if I'm allowed to choose my, if I'm allowed to choose my congruent subgroup and my set of places, there's actually no restriction in assuming that my open set is actually the inverse image of some open set in one such quotient. So I'm actually having, so I can think of my open set as being here. Of course, if I take a smaller open set, this would change my S, change my gamma. That's somehow not my concern at the moment because I'm not quantifying anything. So, and if I have here a normalized adelic torus orbit, it would project to some packet. It would project to some packet of periodic A orbits. And I was talking only about density, but sort of still I would put here some uniform measure on this normalized adelic torus. I would get here some measure. So this attached to it, I would get some measure, which depend on the torus, which is some measure which is A invariant. Now I'm taking, if there were infinitely many toruses which didn't satisfy something I want, I would take their limit. I would get a limiting measure. In general, you have to sort of discuss why I would get a limiting measure, but this is one of these cheats. Like I sort of somehow built it into the statement of the theorem. I took a division algebra where the quotient is compact, so I don't have to worry here about this point. So if I have a sequence of bad tori, which somehow escape from any finite set of fields I'm given, is a sequence of Q tori. Which are somehow bad. And if I have M2 is a limit of these measures of these sort of mu, maybe. For me, always M is a uniform measure on some object, and mu is a mystery measure. Mu is the limit of these measures on the bad tori, then I get is an A invariant measure. Now, I don't know too much about this invariant measure, but I know one thing. So Siegel bounds, Siegel-Landau bounds on class number times, actually not class number, but class number times regulator. And the fact that integers are 1 apart they do give me something in the limit, which is sort of, it's very fortunate that they do give me this particular thing in the limit. They give me that's the entropy of the limiting measure with respect to sort of, let's say it's this, the entropy of this limiting measure with respect to the, for at least some, entropy of this limit measure is positive. Now that's very fortunate. I'm going over time. Because then I can use the measure classification theorem and get that this, at least part of this measure is on some homogeneous thing that I understand. But then there's still a passage to go from there to density, which in fact uses this, my first paper with Barak on homogeneous dynamics. So anyway, now I can wish Peter happy birthday, and thank you all for listening.
Any questions?
Yes, sir.
Is there a setting where there's no zero problem?
That's what the question I was sort of implicitly asking Peter during the talk. I'm not, probably there is, right? I think there's
If you stay away from abelian, stay away from
yeah, so I don't know. So is volume, is this regulator times volume in degree 3 fields? Effectively. Yeah.
Some nice work of Harold Stock shows
Yeah.
certain cases. But the tori are dangerous. Tori are the hardest. The vast number of tori are the hardest. But can you say, well, maybe, this is quite an improvement over what you, the fact that you can say something in general now, before you just had cubic fields, more or less.
Well, I mean, this is something which we had to begin with, but we didn't, like I said,
Another thing kept under the rug, I think.
it appears in our paper, but we didn't somehow, that's sort of one of the reasons I chose this particular thing is to somehow publicize this, because we haven't done a good job at communicating this particular result.
So this is the version like of the degree n the thing that you did for cubing.
Yeah, but it's not equidistribution, only density.
Right.
But
I understand. Now I remember.
Any more questions? Well, then I guess we should take a short breath and have another talk.
I think you cannot do it in less than 10 minutes. Yeah, people need some time.
So in 5 minutes, 7 minutes.
Yeah, 7 minutes. Who's the next speaker? Eskin? 8 minutes. Hey, how are you? שאלתי איפה אתה נמצא. There you are. How are you? How's that? Are you going to show up? Of course. Once every 20 years, I'm making Good? Yeah. Nice to see you here. Nice to see you here. Should be a few more. Jay. Thank you very much. Hey, how are you? Good to see you.
Why I was asking? Look at that. 6, 6. Diagonal group itself intersects in the line. Suppose it is not.
So some conjugate of the